Okay, so now that we've oriented you a little bit to some of the things that we see in our stress strain curves, let's look at some additional features that you'll see on here. So we've seen the strain already here, quite a bit. We'll throw a new one at you. Sometimes you will see percent elongation. Okay, so that is very closely related to the strain value. It might be the final length of the object minus the original length of the object divided through by the original length of the object times 100%. Okay, so very close relationship with strain, as you can see there. We mentioned fracture a moment ago, so let's define that. So the sort of last data point you get on your load versus elongation or on your stress versus strain curve, your last data point represents the last realizable force per cross-sectional area you were allowed to apply to the object before it broke, before it fractured. So this is the fracture point. And if you were talking about the strength meaning the y coordinate here, the fracture strength is also known as the breaking strength, and it's the stress value at which the specimen failed by fracture. Okay, so that would be the y coordinate here for the fracture strength, Fs. Okay, what else do we have at this point? Well, we started with Hooke's law, and we saw that there would be a linear portion to this graph. Okay, so it's a very tall, steep portion on this specimen stress strain curve. And so the linear portion kind of ends about here. So this is what we define as the elastic deformation region. Okay, and this is where we have strong correlations and analogies to our Hooke's law. Okay, so we are linear in the stress versus strain curve up until the limits of the elastic deformation region. Once we deviate from linearity, we transition away from the elastic deformation region to the plastic deformation region. Okay, so all matter can be considered to have these two portions in their stress strain curve, whether we're testing by tension or other load formats such as compression or even shear. You can always expect an elastic deformation region and a plastic deformation region. Okay. Okay, so zooming in now on that transition from the linear portion, the elastic deformation region, to the plastic deformation region. There's a key characteristic there that we would like to have. And so the convention is to actually register 0.2% 0.2% strain to measure that. Okay, so we'll see that in a slide or two when we define the yield strength. Okay. Now that we can focus further here on the elastic region, we define Young's modulus. Okay, so we saw that a moment ago when we looked at Hooke's law. So Hooke's law was characterizing the spring constant for a spring that was extended in a reversible fashion by a strongly correlated force on that extension length. And so here, Young's elastic modulus, capital E, is defined as the rise, the stress value divided by the run, the strain value in the linear elastic portion of the graph. Okay. So, for example, if you were to take a data point here or here and do a y2 minus y1, you could even use the origin, divided through by x2 minus x1, you would be calculating the Young's modulus E. And notice that we will inherit the y-axis units for the units of Young's modulus, since our strain x-axis is unitless, as we show here, millimeters per millimeter, given that we're normalizing to the original length. Okay, so that is Young's modulus. Okay, so to just show you some actual data, we're going to show some of these slopes now in a moment, but I thought we'd look carefully first at something you're familiar with. So here's density, how much mass there is per unit volume of matter. And notice the logarithmic scale on the y-axis to show all these zones where all the data would be for different matter, okay? So you can see metals are located in a roughly different area than polymers, than composites, etc. Notice the log scale. Okay, so here's a moment for you to orient yourself to this rather different y-axis if you haven't looked at one before. Okay, so take a moment to think about this question and choose a true answer, and you might resume the video once you have your answer. 1, do we think glass is less dense than wood? Do we think CFRC, carbon fiber reinforced composites? Do we think carbon fiber reinforced composites is about 10-fold as dense as wood? Or do we think carbon fiber reinforced composites and some steel alloys are about equally dense? Or do we think that wood is about half as dense as glass fiber reinforced composites? Okay, take a moment to find your answer and resume the video when you're ready. Okay, so going through each of these, glass less dense than wood. So here we see glass right here. It's at a value of almost 3 on our logarithmic scale for density here. And then we can see wood is a natural composite, and we see its range down here. So clearly wood is less dense than glass, so this is not the right answer. B is CFRC, about 10-fold as dense as wood. Okay, so let's find CFRC. So here it is. And we want to understand if it's 10-fold higher in density than wood. So its value is here around 2. And so to register a 10-fold change, my exponent has to go up by a whole digit. Okay, so that's how we use a logarithmic scale. So if wood's density is about not 2, but about 1, then this would be a correct answer. So here's 1 down here, and we can see that wood is about there. So that one's looking pretty good at this point. GFRC and some steel alloys, are they equally dense? So CFRCs are right here again. Oh, I'm sorry, I answered for GFRC a moment ago, but CFRCs are right there at about 1.8. And indeed some woods are about there. So the answers I just provided are pretty good. So I still feel good about B. CFRCs are equally dense to some steel alloys. Well, so let's see if we can find steel alloys. So here they are, clearly higher than the carbon fiber reinforced composites. So that one is not right. Wood is half as dense as glass fiber reinforced composites. So the glass fiber, they were around just over that of the carbon fibers, so maybe about 2 there it was, and wood is lower. So again, something like 2 to 1. So this is not a factor of 2. This is in a factor of 10. Okay, so just to orient you to that x-axis. So in fact, it is B that is correct. Okay, Young's modulus, finally showing some values here. Now that you know how to look at this type of y-axis, and we recall that what we're talking about here is our stress versus strain curve, and it's the linear portion of the graph, which may deviate ultimately. And so we are talking about the slope. And so steep values are regarded as very stiff because you have to apply a lot of force per area unit to get small changes in the length of the material, very stiff. materials where you have to apply very little force per cross-sectional area and get a lot of deformation would be not as stiff. So some of the stiffest materials here are going to be up on this logarithmic scale for Young's modulus. And so we are seeing things like glass fiber reinforced composites and carbon fiber reinforced composites being very competitive with some of the most successful ceramic materials and other tungstens and alloy materials like steel.